Hi, welcome to lecture 33. In this lecture we're going to continue talking about the gravity, specifically Newton's theory of gravity, and we're going to relate it back to the gravity on Earth that we've known all along, this mg, right? M times little g being the weight. How does that relate to the law of gravity that we learned about in the last lecture? So here's an overview. We're going to essentially calculate the gravitational force on a planetary surface. Right? We've learned how to calculate it for any two objects. So let's apply that to the specific case where one object is on the surface of a planet. And in doing so, we're gonna, as I said, recover the idea that the weight is equal to m times little g. We kind of will see where the little g comes from. We'll apply that to just do some examples, calculate the acceleration due to gravity on Mars and on the surface of the Sun. But then we'll shift gears a bit. We'll ask, well, how do we know the value of big G, right? The gravitational constant that we introduced last time. Because in all those calculations before, we always assume, okay, this value is known, but how do we actually know it? And it's not so straightforward experimentally. And then we're going to talk a little bit about something called field lines and Gauss's law for gravity. And we're really just going to touch on those. I just want to have mentioned them in this course. We're going to come back to Gauss's law for electromagnetism, or electrostatics specifically, in the future if you continue, with your current physics series. But there are some intuitions that we want to gain right now, and they relate to this idea that we have a law that goes as 1 over r squared. It's a very sort of profound type of relationship in three-dimensional space that crops up again and again. For example, in electrostatics, but also in some other areas of physics. For example, if you want to calculate the intensity of light as a function of distance from a star or some other source. So there's 1 over r squared. There's a certain intuition we can develop here about why those appear to be common in physics. Alright, let's get started. So here's a picture of the Earth as seen from space, sort of. You get the idea. And somewhere on Earth there's our good old friend Sir Isaac Newton, and he's got a little flag. I'm not quite sure why, it just happened. So I want to figure out what's the gravitational attraction between the planet Earth and Sir Isaac Newton. So I might go about and I'm like, alright, well I know gravity, so let's work it out. The force due to gravity is g, that constant, times the mass of the first object times the mass of the second object divided by the distance between them squared. So my two objects, right, are the Earth and Sir Isaac Newton. So I'm going to put m Earth times m Isaac. Now, big M, little m, I don't know, just because the Earth, I guess, is big, right? But there's no reason, there's two different masses. And then, well, r squared. What is r? So those two, I think, are fairly well defined, right? The mass of the planet, the mass of the person. But what's this distance here? Because we're like, well, look at him, he's right on the planet, right? So is distance 0? But that's only true if you look at those rocks right underneath his feet, right? Their distance, 0 or 1 meter from Newton. Right? Another chunk of rock over here is a lot further away, right? I mean, the Earth is a big place, so this might be several hundred miles over. This is really far away. So these rocks over here that form part of the Earth have a different distance. These rocks over here, maybe that, lake over here, the water, each of those bits of mass that make up the Earth have a different distance from Sir Isaac Newton. So what do I do? Now, what you probably, if you think about it, where you probably want to go, just intuitively, you say, well, let's take it from the center. And that's correct. Right, that is correct. But it is not obvious it should be that, right? Or why that should be the case. So the r we're going to use, the r that gives the right answer, is this radius here. That's the r. In this case, because this is the Earth, this is just the radius of the Earth. Right, that is the distance between the Earth and Sir Isaac Newton. He's on the surface of the planet, but it doesn't mean he's got zero distance from the planet. He's got zero distance from those couple of rocks here, right? He's very far from the other side. Now, the fact that we're doing this, we don't just pull this out of a hat. We're like, hey, this seems like an easy thing to do, right? I mean, we test it and, hey, look, it gives me the right answer. Really, what we should be doing is, and you can do this, is that I say, well, okay, I'm going to split up my Earth into lots of tiny rocks. And for each one, I calculate the force. I've got to take care of directions, right? So this rock down here is going to create a force like downwards. This rock over here is going to create a force this way. This little mountain over here might create a force this way. And you add them all up as vectors. And it's difficult. I mean, it requires an integration, a sum of infinitesimally tiny pieces, right? That's what integration is. Over a sphere with the point of reference, in a way, that around which I want to calculate the gravitational force being Isaac Newton. It's difficult to do, right? But, I mean, you can do it. Nothing else. You can plug it into a computer and have a computer do it for you, numerically. And you can show that when you do this, you're going to end up with essentially the same expression as if you just pretended all the mass is at the center of the Earth. Let me write this down. For spherically symmetric objects, it only works because the Earth is a sphere. That's, not heavier on one side than the other. Spherically symmetric objects, we can pretend that all the mass is at the center. In the last lecture, we did stuff like calculate the force between the Earth and the Sun, or the Earth and the Moon, or something like that. Well, in that case, we didn't really ask what part of the Earth and part of the Moon, right? Because the size of the Earth, the size of the Moon were kind of, the size of the Sun even, were small compared to the distance between them, so it didn't really matter whether I measure from the surface or from the center. I didn't really have to worry. But here we clearly do. Like, this is a huge discrepancy. Do I take, the distance to be 1 meter, or do I take it to be 6,400 kilometers? And the answer is, of course, we take the 6,400 kilometers. So we plug in those values, and you can do this, right? I'm going to leave the mass of Sir Isaac undefined. We're just going to leave it as M Isaac, but the mass of the Earth and the G and the radius of the Earth, that they're known, right? And we know what those are. So let's use it. G 6.67 times 10 to the minus 11 newtons per kilogram squared times meter squared. The mass of the Earth, again, this is something we look up, is around 6 times 10 to the 24 kilograms, right? So 6 with 24 zeros, that many kilograms. And the radius of the Earth is about 6,400 kilometers, or 6,400,000 meters, roughly. It could be more precise here. And you take those values and they ask you, just right now pause the video. Right, pause the video, plug in those values, get out a calculator, and work it out. What you're going to find is this. The force of gravity on Sir Newton is, let's write it down again, G, mass of the Earth, divided by the radius of the Earth squared. I'm just going to abbreviate to IME/RE. I know I'm changing my notation a bit, it should be obvious what I'm doing. Times the mass of Sir Newton, right? Same thing here. I just took the M over here because that's the one thing we are not going to plug in a value for. You work out what those values come to. And I ask you to do this, plug in the values. And you're going to find that these come to be around 9.8. So check that it is true. If you didn't do it just now, check it now. Plug in the values. Make sure you pay attention to your powers of 10. You're going to get 9.8 or maybe 9.79 or something like that if you've made some rough approximations. Little g, right? So it turns out that the little g that we've used the whole time in this course, pretty much from day one when we first started talking about free fall, is 9.8 meters per second squared. That is calculated using Newton's law of gravity from g, the mass of the Earth, and the radius of the Earth squared. Now, of course, in practice, people did calculate it, people measured this, and that allowed them to come to conclusions about the values of these. Right, but in a sense, this follows from those values. And that allows us to calculate the gravitational, the acceleration due to gravity on other planets, just by applying the same idea. So let's do that. So here's Mars. This is my beautiful depiction of Mars. The radius of Mars is about 3,400 kilometers, so it's significantly smaller than the Earth, right? It's a little bit over half the linear dimension of the Earth. The Earth is 6,400. And the mass of Mars is 6.4 times 10 to the 23, so that's just a little bit more than a tenth of the Earth. It's a lot smaller and a lot lighter. So let's work out what we get. The force, let's write it out. If you're standing on Mars, notice I drew Mars's little moons here. I take a lot of pride in those. Imagine you're landing on Mars, right? Here you are. You're in a spacesuit. The force on you, force of gravity on you, right? If you've got mass m, is going to be g, that's the same, that's a constant, times the mass of Mars times your mass divided by the radius of Mars squared, because the radius of Mars is your distance from Mars calculated from the center. Right? So you work out what those are, because, you know, we don't want to make assumption about the mass of the person. You work out what those are, and they come to, again, just pause the video, plug in the values, make sure you convert to meters. You're going to end up with something like 3.7 meters per second squared. Right, so this is your value, g, little g for Mars, the acceleration due to gravity on Mars. Again, you probably go to Mars and you can measure it. But if you know the mass of Mars and g, then you can calculate it. Or conversely, let's imagine you fly to Mars and you don't know what the mass of Mars is. How would you know? You don't know what it's made of. Your first time there. Well, you can measure its radius. It's fairly straightforward because you can see it. You can see how big it is. You know the value of g. So if you measure this, you could calculate the mass of Mars. Because depending on what you know, you can calculate the other quantities. But again, the point is the acceleration due to gravity on Mars. The g that makes the weight mg is really just the combination of those values. And for any other object that I'm going to put on the surface, right, I'm changing this one, but not any of those. Now you're like, wait a minute. That's all well and good, but the Earth isn't a perfect sphere. There are mountains, there are valleys. You know, there's the same thing on Mars. Mars has very high mountains. It's a lot smaller, but it has, you know, a 24-kilometer tall mountain that's almost 3 times as high as Earth's tallest mountain. So, I mean, doesn't that, or if you climb on a tree, if there were trees on Mars, I might do it on Earth, right? If I climb up somewhere, like, am I not further away? It's true, but look at this value here, right? Or 6,400 kilometers for Earth, right? If I add 1 extra kilometer because I'm going up a mountain, or even 10 extra kilometers because I'm going up, some volcano all the way to the top. Well, that doesn't change this significantly, right? 3,400 and 3,410, they're really similar. So yes, technically, if you're on top of a mountain, whether on Earth or on Mars, G is going to be a little bit less. But only by a little bit. Now, there are actually measurable effects due to the distribution of mass not being perfectly a perfect sphere, right? So one very famous example is that the Antarctic ice sheets, those many kilometers thick glaciers, they have sufficient mass that they lift up the level of the ocean around Antarctica, right? So, and you can't see this if you go there, but you can measure it with satellites, for example. And so you can you notice that the sea level there is a little bit higher, and I don't know off the top of my head what the values are, but it's measurably higher because the water gets gravitationally attracted just a little bit to those giant ice sheets that have a very large mass. And if or when those ice sheets melt due to changing climate, well, then not only does the extra water contribute to seawater rise, also the water no longer gets attracted to Antarctica in the same way, and so actually it'll rise even more in other places because the water level sinks a little bit around Antarctica. So it's a curious fact there, right? But the point is this: for the most part, for the calculation of G for the mass, whether you go with 3,400 or 3,401 doesn't really matter. So if you climb on a chair, climb a tree, you're changing this insignificantly. You go from 3.7 to 3.69998, right? Something very small that's well smaller than the error in our calculation, the approximation in our calculation anyway. Okay, let's do one more example. Down here I prepared it first. Here's the sun. Try to draw the sun in pencil, which is actually pretty hard because it's a glowing ball of fire. So I decided I'm just going to draw space around it, and this white ball is the glowing ball of fire that we call the sun. So the sun has a radius of about 700,000 kilometers, which is a little bit more than 100 times the radius of the Earth. So you can fit about 100 and something Earths sort of in a long line across the sun. The mass of the sun is 2 times 10 to 30, so that is, about 300,000-ish, a little bit more, times bigger than the mass of the Earth. So it is pretty gigantic. So what's the gravity if you're standing on the surface? Well, let's just work it out, right? We're going to not even write this down, we're just going to calculate G directly. G of the sun is going to be G times the mass of the sun divided by the radius of the sun squared. Now again, pause the video, plug in the values, make sure you convert to meters. If you do that, I think the sort of official value is something like 274 meters per second squared. That's about 28 times the acceleration due to gravity on Earth, right? So if you weigh 100 kilograms on Earth, that's the mass of a I guess fairly large human being, but a reasonable value to take, 100 kilograms, right? On Earth, your weight would be 1,000 newtons. Well, on the sun it would be 27,400 newtons. Right? G would be a lot bigger. So you'd feel about 27 times as heavy. So the big question is, if you land on the sun, will you die because you get crushed by gravity, or will you die because you get burned up? Which one will kill you first? Well, it's not a competition, I guess, but I mean, realistically, you die before you get there, because you're never going to reach the surface of the sun. But if you suddenly sort of teleported there, I suspect that this would kill you in maybe, you know, a tenth of a second or something, whereas the fire will probably kill you in like much faster, because it's so utterly insane. I don't know. Something like that. Anyway, you'd be pretty dead. Alright. So now the question arises. Calculating G on the surface of a planet is this. Now, in practice, you'd go out and you measure this, right? You drop a ball, you watch it fall or roll down a hill, and you can measure G fairly straightforwardly. Let's imagine you're Newton. Well, you know how big the Earth is. How do you know that when you haven't walked around it? People have traveled around it perhaps, but just actually around the time. But really, I mean, people have known the size of the Earth from way before that. The ancient Greeks, at least during the Hellenistic age, they knew it famously. Eratosthenes of in Alexandria, he did the experiment where you take the planet and you stick a stick in the ground here and you stick a stick in the ground here, and they throw different shadows at the same time of day because of their different angle, and knowing the distance between them, you can essentially calculate how big the Earth is just by looking at the shadows of two sticks in different places. So the Greeks knew that, and people knew this value fairly well. The problem is, you come up with your theory of gravity. Well, you don't know the value of this, and you don't really know the mass of the Earth. I mean, how can you weigh the Earth? You can't. Now, if I measure G, what that tells me is, I know R, I know the product of those two, right? So measure G and measure the radius of the planet, which is fairly straightforward, just geometry, a little bit of ingenuity. We can find G times the mass of the planet, right? We can solve for this combination, but we can't solve for them individually. We don't know how much of this is G, how much of this is the mass of the planet, unless you already know G. The problem is, because you don't know the mass of the planet, you can't find G, and because you don't know G, you can't find the mass of the planet, even if you know what the combination is. And looking at other planets won't help you either. So how can we know the value of G? How would Newton have known the value of G? As a first approximation, you might be like, I can estimate the mass of the planet. So strategy 1. Let's write it down first. How can we find G? Because I gave you the value, but Newton couldn't look it up. And looking at little g doesn't help, because we don't know the mass of the Earth. Well, one thing we can do, so strategy 1, fairly sure Newton would have done this at one point, estimate the mass of the Earth. How would you do that? Well, you'd probably use its volume, which you know, because you know its size and you know it's a sphere. Right, 4/3 pi r cubed, volume of a sphere. And then its consistency. Right, you say, what's the Earth made of? I guess mostly rock. And how much is rock? Like, how many kilograms is there in 1 cubic meter of rock? And we call this the mass density. So specifically the mass density. Specifically how many kilograms per volume. If you know the volume, you can figure out the total number of kilograms. And honestly, if you look at a rock, like, you get a fairly good value for it. Now, the inside of the Earth is not just made of rock. It's magma, right? Molten rock, and there's metals inside it. So it's fairly heavy. It's very dense down there because of the high pressure. So it's an approximation. It gives it the right sort of ballpark range, but it's not very accurate. So what's our second strategy? Well, my second strategy is not to measure g, but to just measure the force between two objects of known mass. The gravitational force. Right, the idea is this. If I have the force is g m1 m2 over r squared, well, let's just say I'm gonna put a rock here, I'm gonna put a rock here, I'm gonna measure the distance between them, I can measure the mass of each one, and I can measure the force, maybe I hooked up some springs or something, and I can calculate g, right? Just measure all those other quantities. And in the case of the Earth, I couldn't do it because I can't measure the mass of the Earth. But if I take two rocks, I can do it. The problem with this setup is that the force is completely and utterly tiny, right? For any object for which you know the mass, like a rock or a person, or maybe even a building made of bricks, you just count the bricks. Even then, the force is going to be very, very tiny. It's going to be very difficult to measure. But nonetheless, we can actually measure it. And this sort of insight of how can I very carefully measure that teensy tiny force between two heavy objects, that was due to Cavendish in, I should have looked this up, 17 something or other in the 18th century. Set up the so-called Cavendish experiment now, and here's what that looked like. So here's my simplified picture of the Cavendish experiment. So what you imagine is we have a long rope, and hanging from the rope is a bar, and at the end of the bar, on each end, there's a heavy ball of some kind, maybe a heavy metal ball, like think of it as a bowling ball or something like that, or maybe just some heavy weight. Doesn't have to be circular even. It's spherical, it could be any shape. So heavy weight here, heavy weight here. And then I let this thing just hang, and in practice it'll take a long time to sort of become still if you bump it a little bit. But it has this sort of equilibrium position it wants to be in, because the rope, if you move it, the rope will twist, and then the twist will want to move it back, rotate it back to the original position. And then what you do is you put other big masses next to it, a known distance, right? So I put these big boxes full of sand, I suppose, next to my two spheres. Not touching, but just a small distance away. So these are just some heavy box, right? The other one too. And these are some form of weights. So we just want a bunch of heavy things. So what's going to happen is that the gravitational attraction between this big mass and this other big mass, like M1 and M2, make them both fairly big. Not so big that we don't know what they are, like not a mountain, but fill it with bricks, fill it with sand, something like that. Make it of metal, right? Like a big giant metal ball. And that make the distance between them, the r, fairly small. Right? The distance between our two objects, you make it a few centimeters maybe, to maximize the gravitational attraction. Do it on both sides just to keep this thing balanced, right? We don't have this balance, that's why we're doing it twice, once over here, once over here. Otherwise you just go, if we did it only one side, it just went plonk and hits the floor. Okay, it's kind of annoying. So what's going to happen now is that this ball gets attracted to this box, this ball here gets attracted to this box, and this makes the, very slightly, but it'll make this thing twist, right? And as it twists, the cord, well, it gets twisted, so it wants to untwist, right? You take a cord and you twist it round and round and round and round, it wants to untwist. Now, because it only gets twisted the tiniest bit, that force, the so-called torque, the force causing rotation, the torque created by this twist is very, very tiny. But if I can essentially calibrate how much torque is needed, and again, we haven't talked about torque, but torque is, you know, forces causing rotations. This is a rough definition, but it helps you get a point across right now. You can like measure what torque is created at what angle of twist, and all I have to do is measure the angle by which it twists, and I've measured the gravitational force between this box and this ball, essentially. It was called a Cavendish experiment. Of course, setting this up is very, very difficult, because you want to make sure it really is balanced extremely well, that you know what the masses are, that this distance is small. And your main problem is, if you do this in practice, like I'd love to set this up in the lab, for example, but we can't, because anytime somebody walks past outside, it's going to shake the ground and this thing will start wobbling. And that makes it really hard to measure by how much it is twisted, because it keeps changing. And you can get around it, you can find the sort of center around which it twists, like what is its sort of middle orientation, what's the average orientation it's twisting, but it is fiddly, right? It's very fiddly. Now, nowadays, so this was done by Cavendish in the 18th century, and he got extremely close to the now accepted value of G. Nowadays, we can do this with masses that are really, really tiny in their ongoing experiments, to do this essentially with things of molecular size, right? So this is called microgravity. The microgravity is also used for just to talk about when you're out in space with very little gravity. Anyway, but these tiny forces between small objects, we're getting better and better at measuring them. Doing the calculation is very difficult, but I'm going to post a link to another video by someone who attempts to set this up in the lab, and it ultimately succeeds, but you'll see how fiddly this actually is. Finally, in this lecture, I want to briefly talk about 1 over r squared laws more general, right? Gravity goes as 1 over r squared. If you double the distance, you're going to get a quarter of the force. Now, the way you can visualize these 1 over r squared force is a little bit like this. So imagine this is the mass, right? Maybe it's a planet, and it creates attraction. If I imagine that from this mass, there are spikes going out in all directions. Right, in all directions. You could think 3D here. It's hard for me to draw that. So think of a spiky ball, right? The spikes not just like in a circle, but spherically in all directions. Forwards, backwards, up, down, left, right, and with all sorts of angles. Now, if I imagine I have a little window, and you should imagine also I have lots more spikes than I was able to draw here, right? Imagine I have a little window of fixed size that I'm holding a certain distance from the ball. Right, then I move this window, and I can count the number of spikes that go through the window. The way I've drawn it isn't many, but you can imagine if I draw 1,000,000 spikes, maybe I'll have, I don't know, 1,000 spikes go through my window. Now I move this window twice as far away. Right? And what happens then? Well, I can draw it sort of in 2D for you. Let's imagine this is my ball. And you can imagine those spikes, they do this. Just bear with me right now. Right? They go in all sorts of directions, so I'm just going to focus on the left side here. If the window is this is my window seen from the side. Right? 1, 2, 3 go through. If I go further back, same size window, then maybe, I mean, depending where exactly I draw my spikes, only 1 or 2 will go through. As the spikes have spread out like this, right? So the further you're away, the fewer you're going to catch. Now, if you do it in 3D with a spiky ball, not only would the spikes spread out like this, they also spread out like this, right? Hopefully you can visualize that. So in this 2D example, I'd have that the number of spikes going through my window drops off as 1 over r, 1 over the distance here, because if I go twice as far out, only half as many spikes are going to fall through my window, assuming there are enough spikes, like there are 1,000 spikes and they're equally spaced. But now in 3D, the spikes are only spread out like this, but also like this. So if I double the distance, only half as many spikes fit in this way, and only half as many spikes fit in this way. And so only a quarter of the total number of spikes is going to go through my window. These spikes are what we call field lines. They represent the gravitational field. What's the gravitational field? It's kind of saying like, what if I place a little mass here? What gravitational force would it experience? For example, because there's a planet. And these spikes, they represent their force nicely in the sense that their density, how close are the spikes spaced, represents the strength of the field, because the density of spikes, as sort of exemplified by my window, falls off as 1 over r squared. So anyway, if I've got a 1 over r squared law, and this is in 3D space, that is equivalent to being able to represent my force with field lines. Now field lines, they're not just spiky balls for spherical masses. If you've got a different type of mass or multiple masses, you can use the field lines in very clever ways to get an estimate for what the gravitational field looks like. In the case of, there's a planet here with a moon. Right, what's the gravitational attraction of an object here, given it gets pulled there and there and there, and I can use the spike idea and some simple rules about how they're meant to connect up or not meant to connect up, those field lines, to figure out the shape of the gravitational field, like over here, do I get more attracted this way or this way? I'm not going to talk about this much in this course, but when you come to study electrostatics, you'll be dealing with exactly the same concepts, because in electrostatics, which is the force that, for example, is responsible for the attraction of a proton and an electron going around it, or the repulsion of two electrons from each other, that force, the electrostatic force, also goes as 1 over r squared. So we can, in a sense, philosophize about whether there is some inherent reason that, given that we live in 3D space, we should expect 1 over r squared laws. Or perhaps, more profoundly, is the nature of the physical laws, the 1 over r squared, in some way responsible for the 3D-ness of our space? Now, I could say a lot about these. Some of it makes sense, some of it doesn't make sense, but I want you to just think about these questions. Right? Think about this connection that this sort of spiky ball idea leads to 1 over r squared in 3D space. Now, this spiky ball idea, why am I bringing it up? Well, because it allows us to justify one assumption that we made earlier. And the assumption was that that when I have a planet, and I'm at the surface of the planet, or even just like, maybe a little satellite above the planet, or maybe a moon, that I can pretend all the mass of the planet is at the center, right? So you're going to push all the mass into the center, and I get the right answer for the gravitational force on this object. I can now justify that, because if I've got a mass like this, and it sends out spikes in all directions, and I want to draw it in 2D because it's hard to draw spikes in 3D. Now you can imagine they come towards us, and some will go away from us behind. Attempt it a little bit. Like this in all directions. Well, if you're up here, you count the number of spikes. You don't care whether the spikes started on the surface or whether they started right in the center. Right? In fact, what I can do is I can say, well, look, if I imagine a surface that sort of goes around this this planet, you can imagine this closed sort of spherical shell, right? The number of spikes that goes through it is exactly the same. Everything looks the same on this imagined surface, whether or not all the mass is at the center or whether the mass is in the shape of a uniform ball. And this idea leads to a reformulation of Newton's law of gravity in terms of what's called Gauss's law for gravity. And I'm not going to write it down in terms of you'd need like a surface integral to express it. I'm not going to write this down for you. You're going to meet Gauss's law in a lot more detail when you study electrostatics. And somewhere in that course, hopefully, you'll also come back to think about gravity in this new way. Using field lines, counting field lines in a sense, how many field lines go through my surface, writing this down in terms of the so-called Gauss's law for gravity. So this is really just to give you a hand-wavy justification for why we were able to make the assumption at the beginning that when you stand on the surface of a planet, you take the distance between the center of the planet and your position. But also, I want you just to have seen this idea, so maybe you can think about it yourself, and later on, when you study electrostatics, you will for sure study this idea in a lot more detail and quantitatively. Thanks for watching.